Hello, today me and my group mates will discuss about Beyond 5G as enabling technology for building smart port or Harbour city. Introduction.
First of all, the Beyond 5G stands for Beyond 5th Generation Mobile Network, also known as 6G. In terms of telecommunication, it is an upcoming technology standard for wireless communication supporting cellular network. It aims to take from the Internet of Things to Internet of Everything. Compared to its predecessors, it will be significantly faster by using higher frequencies and higher data rates, thus having higher capacity for data to transfer. It will use sub-mm waves of less than 1 millimeter. It is said that 6G could support up to 1 microsecond latency communication, making it up to 100 times faster than 5G. What is a smart port? A smart port is a fully automated port whereby devices are connected to a network of smart sensors, actuators, wireless devices, and data centers. The key components include communication and computing to increase productivity and efficiency in a port like artificial intelligence, big data, Internet of Things, and blockchain. The characteristic of a smart port. According to a research, the maritime ports have evolved over 5 generations. The first generation includes fundamental service like logistics and transport, fishing, cruises, and emergency rescue. The second generation reduces the dependency on human power. Third generation gives value-added service like distribution, packaging, and warehousing, and it functions as a freight handling hub. The fourth generation creates a network port by joining physically independent ports. The fifth generation of ports, which are the most current, are customer and community-focused smart ports. These features include smart port service and application including vessel and container management. The second category includes technology like automation, networking, and data centers. The third is the application of eco-friendly technology to improve energy effectiveness and lower greenhouse gas emission. Then come cluster management, which are like in a shipping cluster made up of business and stakeholders located close by and whose primary activity is shipping. The creation of hub facility is a crucial last step in encouraging cooperation between ports.
Function of Beyond 5G. Firstly, let's start with autonomous vehicle. Connectivity for all things is the most crucial driving characteristic linked to the next decade of lifestyle. Using Beyond 5G as a platform, an order of magnitude or even higher number of planned interconnectivity and widespread use will be another defining characteristic of the future society. This will include infrastructure essential for the smooth functioning of the community that we have become used to today. In the case to have a smooth function, we need smart port. Besides this, smart ports will analyze data to create a more risk-free environment, and having these informations in real time can result in a safer working environment for autonomous vehicles. Hence, smart port is important for autonomous vehicles with beyond 5G as the smart port enables the autonomous vehicles to run in all weathers, cost effectiveness, and time efficiency. With smart port, autonomous vehicles enable an even faster connection between transport systems. The Beyond 5G network will offer a new applications option advancing the development of autonomous car. They will be able to make independent decisions in the future and communicate and cooperate with other autonomous vehicles. In addition to this, the increased reliability of the sensor monitoring with the help of smart port is also essential to successfully migrate toward a truly connected society. Industry 4.0 or the fourth industrial revolution with wireless technology in smart manufacturing already exist. Unfortunately, there is still a real problem of overlapping of specific frequency bands will result in partial blocking of frequency or interference. Hence, to improve connectivity issues and create small scenarios where cloud computing and artificial intelligence can be applied to manufacturing, we need beyond 5G to bring new possibility to the industry. Li Peigen, the academician from Chinese Academy of Engineering, believes that because of a high-precision manufacturing process can entail accessing tens of thousands of sensors, it is vital that wireless communication technology features high reliability, massive connectivity, and ultra-low latency, which all beyond 5G does. Currently, most smart factory rely on wired connections. However, deploying the hardware needed for wired connections is complex and time-consuming. Function of smart port in Industry 4.0 is that the automatic identifications and detection of the container in the smart port will help the port increase handling capacity. Therefore, Beyond 5G is essential in this case because by using Beyond 5G, it's unable to communicate with capability almost equal to wired connection but with greater flexibility. Since the early days of 5G trial, the technology potential to transform the medical sector has been frequently cited in scenarios ranging from remote diagnosis to remote surgery. Although the surgical procedure performed remotely over mobile network is still likely many years away, plenty of applications using more modern network technology and systems are being rolled out globally alongside many other trial projects. But the researchers believe that beyond 5G can solve many of the problems that have prevented the broader uptake of telemedicine. In the aftermath of coronavirus pandemic, researchers believe that beyond 5G technology will enable remote healthcare support and reduce patients exposed to contagions by minimizing in-person visits to doctors or healthcare facilities. For patients who can't easily travel to healthcare providers, Beyond 5G will allow the provider to visit them via immersive telepresence system. According to the researcher, the COVID-19 pandemic has made people realize the advantage of telemedicine and reducing the risk of spreading the virus by traveling to hospital. Medicine also can be delivered to their front door. Beyond 5G or 5G also provide the basis of experimentations into advanced use of such as surgery performed remotely by experts using robotic arm connected through communication network. By using Beyond 5G in e-health, it will benefit both sides of the patients and medical sector.
Transforming the above functions of Beyond 5G into a smart pod is not an easy feat and comes with its own challenges. Beyond 5G brings with it numerous exciting applications and services. Therefore, designing a network at such high frequency must have multitudes of roadblocks and challenges that the researcher have to tackle in order to develop a wireless network that can deliver on its promises and meet the expectation. 6G evolution focused more on the densification of the tiny cell network. There has been limited spatial modeling of the potential rollout of new technologies, while the invention of 6G also focused on the spatial rollout of telecommunication technologies over time. Delivering 6G relies heavily on network densification and more other spectrum. Therefore, it will bring a big impact on the economics of delivery. Besides that, it also restricted the modeling of spatial and temporal dynamics of the rollout for 6G. Secondly, the evolution of 6G requires a higher cost. The cost modeling of 6G enables comparison between data traffic demand and network costs in various types of scenarios. Thus, the necessity of throughput density, periodic interest rate, and tiny highly dense base station infrastructure investment has a significant impact on the cost of 6G infrastructure densification. Due to the massive connectivity, 6G invention expect a higher quality service to handle the higher traffics. According to the industrial IoT enthusiasts, there will be billions of devices will be connected to and being used in the future industrial ecosystems. For instance, comparing the connection density for 5G, which is up to 1 million devices per square kilometers, 6G is stated to enable up to 10 million devices per square kilometers. With the massive number of devices present, the network could end up being overwhelmed and congestion could occur. Also, the slow retrieval and sending of data could lead to slow logistics and slow productivity in the pod. This can cause bottlenecks to not only the pod, but global supply chain as well. Other than that, smart pods also integrate more automated systems such as autonomous vehicles. This would require real-time communication with zero delay and minimal latency to communicate with one another with accuracy. Otherwise, it would disrupt the chain. Thus, it is important for a smart pod to have a higher throughput and efficient congestion control to handle the enormous volume of transactions in real time. Thereby, it will be a challenging task to adapt the 6G architecture for unpredictable traffic usage.
Beyond 5G, communication interference is one of the challenges that Beyond 5G in SmartPod might face. Beyond 5G is a wireless network which makes it more prone to interference. In a SmartPod, obstacles such as container can hinder radio signals from reaching certain areas. These hidden areas can cause packet loss. In other words, data is unable to reach its trajectory point, causing loss of data that may be crucial for the pod to operate. Containers and other large infrastructure in a pod, like the key crane, also cause other problems like reflection, scattering, and non-line of sight communication. This is due to these infrastructures being made of steel and placed closely together. For example, the path between the container stacks is usually 25 to 30 meters wide. connectivity. Other than that, the presence of static and mobile obstacles due to massive connectivity can cause dynamic and unpredictable operating environments for mobile items and equipment. Another thing might hinder the connection in beyond 5G is the terahertz waves. Short wavelengths of terahertz means that they can only travel for short distances, unlike previous 3G or 4G, which have longer wavelengths. Fifth challenge would be efficient energy and resource management. As sustainability becomes a more common topic, beyond 5G aims to be more sustainable than before, and thus will require less power use and networks to have energy-efficient mechanism. This poses further challenges due to the massive connectivity demands and the amount of devices required in a smart pod. Security such as confidentiality, integrity, availability, and authentication and access control poses an important challenge for beyond 5G in a smart pod. In a beyond 5G wireless connectivity, encryption techniques such as symmetric key encryption algorithm requires lightweight for lower power IoT devices. However, the lightweight cryptographic techniques may expose data which can cause a privacy risk due to computational restriction, thus breaching confidentiality. For integrity, when there is a massive volume of data produced and sent, eavesdropping and modification of the data can occur during transit instead of its intended behavior. Additionally, the large volume of interconnected devices expands the risk of DDoS attacks, and speciality of current network security tools before 5G, for example, cannot be applied into beyond 5G. Moreover, authentication and access controls are important so that when data are in transit or stored, they could not be easily manipulated without authorization. Since current conventional centralized authentication and access control mechanisms are unable to match the demands of scalability in 6G. Any breach or threats from these can disrupt the chain of operations in a smart pod. Hence, other principles, protocols, and mechanisms in beyond 5G needs to be changed and tailor designed for these systems.
And architecture changes after implementing beyond 5G. In order to improve the competitiveness and productivity of a smart pod when implemented beyond 5G, the following applications can be deployed. Smart marine traffic management can be designed to manage the navigation of maritime traffic and ensure its safety of maritime traffic. Both land and sea intelligent transportation systems can be integrated to provide a holistic solution that can smoothen the traffic flows on land and sea, which is important in busy ports. Smart logistics can be designed to track, monitor, and manage traffic, logistic, containers, and inland depots in an adaptive manner in order to optimize the local and global supply chains in an unpredictable and dynamic environment. This is because the right inputs in terms of quality and quantity must be provided to the production and manufacturing systems at the right times and places in order to facilitate Industry 4.0. Equally important is a smooth flow of goods to customers. Smart security services can be designed to ensure the availability, integrity, and traceability of data, information, and systems, and the presence of malicious entities in order to optimize the security of the smart pods. While security services such as video surveillance, face recognition, trajectory tracking, and RFID-based electronic seals for securing containers have been proposed. RFID-based smart gates, security services, and best practices can be proposed to secure the above new applications. For instance, the AIS, maritime traffic, and logistic data and information can be manipulated by heterogeneous, malicious, and network entities, equipment, and infrastructures, affecting marine traffic and resource management. 6 GHz 5th generation wireless network are being deployed around the world. The primary physical layer technology used therein is massive multiple input, multiple output operating in sub-6 GHz frequency bands. While wave communications were originally designed to be one of the 3 key technologies in 5G networks, but this has not yet been widely adopted. Its susceptibility to obstacles, lack of coverage, and several path loss are major obstacles to wave communications. However, 6G and beyond communication are expected to support cutting-edge applications such as immersive virtual reality, high-fidelity holographic projection, digital twins, connected robots and autonomous systems, industrial Internet of Things, intelligent transportation systems, and brain-computer interfaces.
These applications demand extremely high data rates, extremely high dependability, and extremely low latency, all of which cannot be easily provided by the current systems. These applications also have high quality of service requirements. Communications in the wave and even terahertz bands will unavoidably become more prevalent given the significant amount of bandwidth that is accessible at high frequency. Massive MIMO techniques already gains at base station reduce path loss at high frequency but are unable to address the obstruction issue. Blockages can be removed and coverage gaps filled by more densely placed base stations. But this is an expensive option in terms of infrastructure as well as power consumption. Therefore, to address this issue, a new cost and energy efficient technologies are required. Reconfigurable intelligent surfaces, a major enabling technology, have recently been proposed as a means of avoiding the aforementioned problems. In order to reflect radio frequency radiation over obstructions and provide a virtual line of sight propagation path between a wave source and the destination, RS can be mounted on substantially flat surfaces such as walls or ceiling within buildings and signage outdoors. Changes expected to the OSI layer in order to support beyond 5G. A conceptual framework for describing the operations of a networking system is called the Open System Interconnection Model, also known as OSI model. The OSI model categorizes computing functions into a global set of guidelines and specifications to promote interoperability between various hardware and applications. The connections between computing systems are divided into 7 distinct abstraction levels in the OSI reference model, which is physical, data link, network, transport, season, presentation, and application. To describe each layer in a simple way, the physical layer transmits the original bit stream on a physical medium. The data link layer defines the format of the data on the network. The network layer determines the physical path that the data will take. The transport layer uses transport protocols including TCP and UDP. The season layer maintains the connection and is responsible for controlling ports and seasons. The presentation layer ensures that data is in a usable format and is where data encryption occurs. And finally, the application layer is the human-computer interaction layer where application can access network services.
Of course, when implementing a whole new technology that is far superior from the previous generation, some changes will be inevitable, and these are the changes. Through research, one of the changes that researchers suggest is a change to the transport layer in the OSI layers. The change being utilizing machine learning to improve congestion control in TCP over wireless networks. This is due to the current TCP congestion control works fairly well in cases of wire connections. However, in wireless cases, packet losses are usually caused by error in the link, and TCP has no mechanism to distinguish whether it's congestion or actual packet loss. This reduces the overall throughput of TCP over wireless links and is the reason why wireless links are usually slower than it can be. Hence, the machine learning algorithm will be able to determine the cause of a packet loss only from the information provided at the end system. It will then classify the packet loss, and then modified protocols will perform accordingly. Each time a packet loss is classified as a triple duplicate, its cause will be determined as packet loss. If the loss is classified due to congestion, the sender will proceed as usual, or multiple changes to data link layer. Under the data link layer, we have multiple access techniques or multiple duplexing mechanism. In layman terms, this layer helps to link the connection between devices. It determines how many and which users get to send or receive information and the amount of resources given to them, including time, frequency, and space. With 6G wishing to increase its sharing capacity due to massive connectivity, researchers propose using free duplex. Previously, from 1G to 4G, full duplex was used. It includes two types called frequency division duplex and time division duplex. Frequency division duplex dedicates two entirely different frequency bands for the connection uplink and downlink in the same time frame. For time division duplex, they will use the same frequency, but information shared and received can only happen one at a time. Hence, the entire bandwidth is used, making it a slow option. However, in free duplex, it plans to eradicate the differences between time division duplex and frequency division duplex. allowing flexibility and self-adaptive scheduling to utilize the spectrum resource based on necessity of the three domains: time, frequency, and space, hence allowing spectrum resource allocation to be more effective and efficient. It also increases transmission rate and throughput in 6G as well as reduce transmission latency. Lastly, for the physical layer changes, researchers propose a change to the medium that the B5G or 6G will be transmitting its signal. The change is to utilize the upcoming and promising terahertz communication. 5G wireless network uses millimeter waves, which are roughly around 24 GHz to 54 GHz, but terahertz will be an attempt to combat that by having its transmission well over 300 GHz with a peak data rate of 1 terabit per second. This is a great addition as it means the overall rate of wireless data transmission will be extremely fast, resulting in basically real-time data. With that being said, it is particularly important for transmitting large quantities of data to support real-time data analysis. The ability to access real-time data analysis comes with great benefits such as smoother operations and faster decision making, which are both beneficial to a smart port.
The spatial model conclusion, we can see how the Beyond 5G technology can help in developing smart port and harbour cities, but implementing it, we have certain challenges like limited spatial modeling of the potential rollout of new technology, high cost, massive connectivity with high quality service to handle high traffic, communication interference, good communication, and the security of Beyond 5G. Other than that, the function of Beyond 5G can be implemented in areas with autonomous vehicle with high safety dependency on reliability and latency, as it will provide a more risk-free environment and increase handling capacity with the automatic identification. The architecture change in 5G is that it supports cutting-edge applications now. Applications such as immersive virtual reality, high-fidelity holographic projection, digital twins, connected robots and autonomous system, industrial Internet of Things, intelligent transportation system, and brain-computer interface. Besides the architecture change, when we implement Beyond 5G, there are several changes in the OSI layer, which are the transport layer, data link, and physical layer. Finally, we can say that the Beyond 5G will bring a new avenue to both the present and the future of smart port.